All right, guys, we're just continuing with the practice final exam. Okay, we're up to question 31 out of 50. Um, Remember, your final exam will be 45 questions, I think it is, for honors and 40 questions for general. This practice one is 50 questions, so a few more questions, but again, same concepts and stuff being tested. All right, so we go to 31. It's just asking us what type of reaction this is. And we got to be a little bit careful, right? Hopefully, we know it's double replacement. And that's the answer, right? We got two ionic compounds, two ionic compounds. What happened? The nickel and the sodium switch places, right? So a basic double replacement reaction. But what we want to be careful about is remember, double replacement sometimes, instead of double replacement, it might be a precipitate forms or precipitation. Um, and we did get a precipitate. So maybe if it was precipitation reaction, they wouldn't give you both double replacement and precipitation or double replacement and acid base neutralization, right? Acid base, special type of double replacement. And not every time a precipitate forms, it's double replacement, but usually when we're thinking double replacement, we're thinking either acid base neutralization or we're thinking, two solutions mixed together in a precipitate forms. So just watch out for those types of different types of vocab. Okay, kind of describing the same thing, but yeah, it's double replacement. Okay, um, right. But it maybe they just say, hey, what's the precipitate? It would be nickel 3 phosphate here. Okay, so yeah. All right. Uh, Move on to the next question. Okay, which of these metals would be able to replace magnesium in a single replacement? Remember, that's an activity series question. So basically, it's which of these metals are above magnesium on the activity series, and you don't have to have that memorized. Whoops, we want to go to the periodic table in our formula sheet, right? So we have our activity series, but we don't want to look over here. We want to look at the metals, sorry. So we want to look here, and it was what can replace magnesium. So here's where magnesium is. Anything below it won't be able to replace it. Anything above it will. So the ones that can replace it are sodium, calcium, potassium, lithium. Let's go back and see what our answer choices are. Um, so it was calcium is the only one above it, right? Um, so again, just activity series. You don't have to memorize it. The halogens is the same order on the periodic table, but you still have it for the halogens and the metals. Remember, metals are going to replace other metals in single replacement reactions, or maybe hydrogen. Okay, hydrogen's kind of behaves like a metal when you're talking about single replacement because it's either H or it's H plus, right? So, or H2 or H plus, just like a metal is like sodium or sodium plus, right? So, um, for single replacement, like replaces like. So if you have a halogen is going to replace another halogen. So like fluorine replaces chlorine, right? But if you have a metal or hydrogen, metals replace metals or hydrogen, right? But only if it's above it on the activity series. Okay, so zinc can't replace magnesium because it's not above magnesium on the activity series. If we go back, I think gold, mercury, and zinc, if we go back to the periodic table, zinc is below magnesium, gold is below magnesium, and mercury is below magnesium. So they're all below magnesium, so they can't replace magnesium. So the only one that was above it was calcium. Okay. So moving on. All right. So we got our mass number for each isotope, and we have our percent abundance, and we want the average atomic mass. So all we do is take this number and multiply it by this percentage, this number, multiply it by that percentage, this number, multiply it by that percentage, and then we add them all up. Now, if we keep the percentage as this form, 78.25, then after we add them all up, we have to divide by 100. Or we need to, when we multiply this mass number by this percent, we need to multiply by that 0.7825, not 78.25. And if we do this by 0.7825, and then that remember, so we're just dividing by 1,000 or moving the decimal place to the left twice. So what you would really want to do is this times that, this times that, this times that, and then you add them all up. And that's how you get it. And the units for atomic mass or average atomic mass are atomic mass units, AMUs. All right, so let's see what I did. All right, so this times, and again, I didn't do times 78.25, I did by 0.7825, and that's this number. And then I multiplied these two together, and then I multiplied these two together, and then I added them all up, and it came out to be 23.55 atomic mass units. Okay, so that's really all you have to do. Remember, it's a weighted average. Let's see if we could do process. I'm gonna put this back so I don't save the edited version accidentally. All right, so let's see if we could maybe figure it out. Right, so we have a mass number of basically 23, 25, and 26. And we got a lot more 23 than we do 25 or 26. So we should probably be picking a number closer to 23 than it is to 25 or 26. So yeah, maybe if 25 and 26 were a little bit more abundant, that's a possibility. Hopefully you can eliminate those two. And really, if you had to guess, you know, the weighted average is going to be closer to that with these percentages and a lot further away from that. So probably could have done it in your head. And again, this is an impossibility, right? The average atomic mass has to be in between 23.01 and 26. So it can't be 33, it can't be 29. Okay, so B and C would just not be correct guesses. All right. All right, moving on to the next one. All right, so calculate the amount of heat released when 100 liters of HI are created during a reaction at STP. So it's stoichiometry with delta H. All right, so what this delta H for this reaction is saying is when 1 mole of this reacts, this is how much energy you get. When 1 mole of this reacts, this is how much energy you get. And if 2 moles of this are produced, this is how much energy you get. So it's this much energy for 2 moles of HI. That's the important ratio, okay? So what we first got to do is take what we're given, 100 liters of HI, and convert it to moles. Well, when we have a gas at STP, remember, we just divide by 22.4. And then once we have moles of this, we're going to multiply by this number and then divide by 2 because it's that much energy for every 2. Now, we don't need 2 moles of HI. We don't need the negative sign because negative energy just means it was released or produced or lost to the environment. So since the question asked how much heat was released, we already know the energy value that we're going to report is an energy being released, so we don't need the negative sign. If this had said, what's the energy change when 100 liters of HI are produced, then you would have to have the negative sign if it's exothermic, which it is. So for this question, you would need the negative sign. And if it had been an endothermic reaction and this number was positive, then you would need the positive sign if it was an endothermic reaction, okay? But you don't need that, right? So it's just this much energy for 2 moles of HI, that's the ratio, and that's what we got to do. So setting it up, whoops. All right. We would take, here's the setup. Sorry for my bad handwriting. We take our 1 liter, divide by 22.4. That cancels out liters and gives us moles of HI. And then again, according to the balanced equation, it's this many kilojoules for every 2 moles of HI. So don't forget to divide by 2. And it comes out to be 54.4 kilojoules when we do our math. And again, if this said, what's the energy change, then we would need the negative sign. But odds are, if you see a question that asks you an energy value where you have to have the right sign, whether it's positive or negative, you'll have 2 choices. One would say negative 54.4, and the other one of the answer choices would say positive 54.4, and you'd have to know which one is right. So if you saw 54.4 or negative 54.4 in this question, that's when you have to know, oh, well, wait, was energy released? So it should report a negative energy value, or is energy being absorbed? Should I report a positive energy value? Okay. All right, moving on to the next one. All right, so we got stoichiometry, and it's limiting reactant stoich because they gave us two amounts, right? So it's asking how many moles of silver sulfide will be created if 12.5 moles of silver react with 9.0 moles. So the reason why it's limiting reactant stoich is they gave us an amount of both reactants. Usually they would give us this amount of silver and say we had excess H2S, or maybe they give us this amount of H2S and tell us we have excess silver, but we don't. We have this much H2S, we have this much silver. So, and we want to know how much of this product is going to be produced. And it's moles. So really all we have to do is take this number, moles of silver, and multiply it by 1/2. And then we have to take this number, 9 moles of H2S, and multiply it by 1/1. And whichever the smaller value is, that's the right answer, right? And that's going to be our limiting reactant and all that stuff, all right? So if I take the 12.5 moles of silver, this is how many moles of silver sulfide I should be able to get, 6.25. So I have enough silver to make 6.25 moles of that, right? And then if we do the same stoichiometry, but with H2S, remember now it's a 1-to-1 ratio, right? 1-to-1, okay? We would take our 9 moles of H2S, multiply it by 1/1, and that means 9 moles of Ag2S, right? So we have enough hydrogen sulfide to make 9 moles of this, but we only have enough silver to make 6.25 moles of this. So the answer is 6.25. That's how much we can make, and the answer is D. Okay. So a little limited reactants there. All right. So here we have 3 different measurements of the same thing, and notice they're all very close to each other. What does that mean? It means we were precise. Our data is precise. And then they tell us the actual value, and our measurements are very close to the actual value. So it's also accurate. So the answer is precise and accurate, accurate and precise. So again, you need to know what the true value is in order to know if you're accurate or not. To know if you're precise or not, you just need to compare your values to each other. So if you've only taken one measurement, if you've only done one trial, you can't know about precision until you do multiple trials. Okay. All right. All right, so let's see if I have any notes on that one. No, okay, pretty straightforward. Okay. Next question. All right, so we have some water molecules and they're interacting with each other. We should know that that's a hydrogen bond. Okay. And that's what the question's asking. Okay, so we know water's polar. We know it has dipole-dipole interactions, but those dipole-dipole interactions are the special type that we call hydrogen bonding. So hydrogen bond. Remember that the hydrogen-oxygen bond there, that's a hydrogen-oxygen polar covalent bond, but that's not what a hydrogen bond is. Remember, it's positive dipole to negative dipole. It's a dipole-dipole interaction, but just a special type, okay? Let's see if I had any notes. Right, yeah, special type of dipole-dipole interaction, hydrogen. Okay. And I'm guessing that should say chemical bond, and it's not a chemical bond. A chemical bond is a covalent bond or an ionic bond within a molecule. This is an interaction between molecules, okay? All right, we move on to the next one. All right, so we got a nuclear decay equation here, and we just got to figure out the particle. First, let's just review, right? That's a neutron right there. That's a gamma particle. Notice 0 and 0. So that's gamma radiation. This is a beta particle. Technically, it's beta negative, but we call beta particle an electron. So that's an electron, beta particle. And this is an alpha particle. So it's basically which one of these fits here, and it's just balancing the equation. Remember, this is an equal sign. So the missing number on top is 4, right? Because 235 minus 231 is 4. And so we know the answer is D, okay? And then if we do 92 minus 90, we get 2, right? And then how do we get the symbol? Atomic number 2 on our periodic table is helium. So that's where the symbol comes from, okay? So this was alpha decay. Yeah, right. So here I have everything circled just to remind you what the particle is, but the actual, answer is D. That's an alpha particle. Okay. Remember, alpha particles are positive. That maybe sometimes comes up. Remember, and Rutherford used those particles in the gold foil experiment. Okay, so we have an organic molecule here. Hopefully we notice that OH group's an alcohol group or a hydroxyl group, if you want to call it that way. But we also have the carboxylic group, carboxylic acid group, or carboxyl group, which is the double bond O and the OH on the same carbon. Okay. But this is asking about VSEPR theory, so the shapes around the different carbons. So the middle carbon has 4 bonding domains around it, so it's tetrahedral. But the carbon on the far right, this one, has only 3 bonding domains, so it's trigonal planar. So these 2 carbons are tetrahedral. This carbon's trigonal planar. The oxygens, this would be a tricky one. Remember, the oxygens, all of the oxygens have 2 unshared pairs that aren't drawn. So if they ask you the shape around this oxygen or this oxygen, and you said linear, you'd end up being wrong. It's bent because there's 2 unshared pairs here, and it's really not 180-degree bond angle. It's really around 105, right? So be careful about that one. But for this one, this carbon is tetrahedral and this one's trigonal planar. So be careful. It's trigonal planar. Whoops. Not trigonal pyramidal. So the first one's tetrahedral, the middle one there, and the second one is the far one there is trigonal planar. Okay. Next one, we got another carboxylic acid. So hopefully, remember when they write OOH, when they write OH at the end, you're thinking alcohol. When they write OOH at the end of organic compound, carboxylic acid, organic acid, carboxylic acid, that kind of thing. So we know it's a carboxylic acid. And remember, whenever you have anything other than carbon and hydrogen in an organic molecule, you're going to be polar. So carboxylic acid, polar. All right. Yep. All right. So a little bit more organic chemistry here. Which ending is used when carbon chain contains at least one triple bond? Alkynes, right? Alkynes, triple bond. Alkanes, all single bonds. Alkene, you have at least one double bond. And alkyne, you have a triple bond. What does OL mean? Alcohol, right? Okay. Yep. All right. An ion, so they're telling you it's charged. And remember, when it's charged, that means you have a different number of electrons than protons. So we have 52 protons, we have 74 neutrons, and we have 52 protons, 74 neutrons and 54 electrons. So because we have more electrons, we know it's -2. So we can eliminate choice C, right? It's not a +2 ion, it's a -2 ion. So this has the right charge, this has the right charge, and this has the right charge. Okay. Atomic number is always protons. So now we can eliminate choice B. So because we know we have to have 52 for our atomic number. So choice A or choice D. Okay. Choice C and B have been eliminated, right? And then how do we get our mass number? The mass number is not the number of neutrons. The mass number is protons plus neutrons. So we got to do 52 plus 74. And so the correct answer is A. Okay. Right. If we wanted to write it in isotope notation, right? Mass number 126. Again, how do I get that? 52 protons plus 74 neutrons has a mass of 126. The number we always put here is the atomic number. So number of protons, 52. And then if it's charged, right, we put the charge up in the right-hand corner, and the charge is 2- because we have 2 more electrons than protons. And how do we get the chemical symbol? Well, we go to our periodic table and find number 52, beryllium. Okay. All right. Number 43, what would be the pressure in atmospheres? 40 grams of nitrogen gas, 300-liter tank, 450 Kelvin. Okay, so we're given the amount of gas, we're given the volume of the gas, and we're given the temperature of the gas, and we want to know pressure. So ideal gas law, right? PV equals nRT, we're solving for P. But remember, our N value in PV equals nRT is moles. So we're going to have to convert the 40 grams of nitrogen to moles of nitrogen and then just plug everything in and solve for P. And we just have, the other thing we have to worry about is making sure to use the right R value. So if we go to the back of our periodic table, remember you get your R values and you got 3 of them to choose from, and you would be choosing this R value, 0.08206, because you want the pressure to be atmospheres, okay? If they wanted the pressure in millimeters of mercury, it would be this one. And if they wanted kPa, kilopascal, it would be this one, right? So I think I have it worked out here. So the first thing to do is take your 40 grams of nitrogen, divide by 28.02, which is the molar mass of N2, 14.01 plus 1401. That gives us our mole number. So we're using PV equals nRT, so that means P equals nRT over V. Plug in our moles, plug in our R value, plug in our temperature in Kelvin, which already was 450, 30 liters, and we get 1.76 atmospheres for our final answer. Okay. We'll keep going. Which of the following substances is an electrolyte? Conducts electricity. So salts, so salts and acids, right? Whether it's weak or strong. Remember, weak acids are weak electrolytes, but that doesn't really matter. It's an electrolyte. So here's a salt, and don't forget that's a salt. So those two. Hydrocarbon wouldn't be very water soluble. If it was soluble, it wouldn't produce ions, so it wouldn't conduct electricity. The same thing with CO2. CO2 doesn't produce ions in solution, so it's going to not conduct when it's dissolved. So it's just going to be 1 and 3, 1 and 3. There you go. All right. So if we look at it, right, so you're just looking for ionic compounds and acids. So like if acetic acid was on there, that would be a weak electrolyte. HCl would be a strong electrolyte because it's a strong acid, but I wouldn't worry about that differentiation. But the main one would be, hey, if it's a salt, it's going to produce ions in solution, and that solution is going to be able to conduct electricity. All right, moving on to number 45. All right. Which best explains why an atom of calcium is larger than an atom of bromine? So we know that if we look at our periodic table, we know that atomic radius decreases as we go left to right. So if we notice, bromine and calcium are in the same row, and bromine's further to the right, meaning bromine is a smaller atom, has a smaller radius than calcium, right? Because atomic radius decreases going this way, right? Even though bromine is a lot more massive, like one atom of bromine weighs almost 80 AMUs, whereas one atom of calcium only weighs 40. But calcium still takes up more space. Its electron cloud is more spread out. Now, why is that? Bromine has 35 protons, plus 35 in the nucleus, and calcium only has a plus 20. So with that extra 15, plus charges in the nucleus, that increases the attraction of the electrons to the nucleus, and it pulls them closer. So again, they both have the same number of energy levels, right? They're in energy level 4, row 4 in the periodic table. Their valence shell is 4. So they have energy levels 1, energy level 2, energy level 3, energy level 4. That's their electron cloud, right? So they have the same number of energy levels of electrons, but bromine has a plus 35 nucleus and calcium's only plus 20. So those 4 energy levels in bromine are going to be pulled closer to the nucleus and thus making it have a smaller radius. All right, let's see what our answer choices are, but that's basically it. So 4 energy levels, bromine only has 2, nope. Calcium has fewer electrons, nope. Calcium forms negative ions, nope. Calcium has fewer protons. There you go. That's one. Choice D. All right. All right. So I know we're close. We've got 5 more to go. But I got to cut it short because I got class starting here in about 5 minutes. I'll finish up with another shorter, hopefully shorter video. We'll see. For the last 4 questions on the test, or 5 questions. 46 through 50. Okay, so hopefully this is helping you get prepared for your final exam. And one last video, to wrap up the year. All right. Have a good one.